Yeah. Okay, so this week we're extremely happy to have Afif Omar, who's a patient candidate working at University of Victoria with adverts. Yeah. But work is doing here, so it's doing between Carlos Lima and Douglas Sandler. He's in the area at Carleton, so we decided that we wanted to have him come over and tell us about probing dark forces with polarized beams at Bell. So
Yeah, thank you very much. I'm very happy to be here. It's decent, very beautiful despite the weather right now. Makes me feel right at home. Yeah. Yeah, so this is work mostly based on this paper that has come out somewhat recently. And yeah, I guess I'll start with a bit of an outline for what I'm going to talk about. This is better. Yeah, so I'm just going to start with a bit of motivation, some background, why do we care about this whole thing? And it's mostly I'm going to describe there's dark forces in the title. Okay, what are they? Just a little bit of what evidence do we have for them, things like that. Then I want to spend a little bit of time just to introduce the Bell 2 detector. And specifically, I want to talk about the chiral Bell proposal. What is that? And then I want to go back a little bit, talk more about dark bosons, describe a little bit more about the theory, what it is, and just a few different models that we look at. Then finally, I hope to bring it all together, both the dark bosons that I've described, chiral Bell, and then okay, how can we see those things using chiral Bell? And also using the regular Bell. And yeah, giving you here a bit of a spoiler. There's also a spoiler in the title about what chiral Bell is. But yeah, the main signal that we are going to be interested in is observing single photon in the detector. That's going to be the signal we're going to be looking at. So I'm going to describe the backgrounds, and then with a good understanding of that, and see what each one is. Okay. So just a bit of background. Okay, why should we look for dark forces? Dark forces, they can be a mediator that connects your dark sector with the standard model. This mediator itself, if it's long-lived, could also account for dark matter. And of course, you don't need me to tell you dark matter, very important to understand. It's like most of the matter in the universe, 85%. So yeah, it's just, we should know what it is. And there's lots of evidence for dark matter. Just like a little sample here of all the different things that people have seen for what dark matter is. So for example, up here, there's velocity, velocity dispersion. So some evidence for dark matter using, for example, the virial theorem. This was one of the first, thing people have looked at to see that there's more stuff than we can see. There's things like the bullet cluster where you have the clusters, then that's the baryonic matter, or the luminous matter is the stuff in red. And then if you actually model how this happened, you would expect that there's actually a bunch of matter that where the blue blobs are, and that's because dark matter is not strongly interacting, it's kind of gravitationally interacting, and so kind of trail behind. And yeah, so there's a bunch of things. There's gravitational lensing from galaxy clusters as well. You can see this smooth background that will explain nicely with the dark matter halo. And of course, there's the galaxy rotation curves where if you only account for the stuff that you can see, this is what you would expect to see, but just from the luminous stars. But what we actually see is the thing on the left, which is explained nicely by a bunch of dark matter. There's more. So this is just a sample. There's of course evidence from the CMB. If you look at the CMB power spectrum, the relative heights of the peaks here can tell you the fraction of matter content that you have. And here, like, for example, if you're play around with this, you'll find that the matter content that matches what's observed, which is somewhere here, then gives you a spectrum that is the thing that we see. Okay. So yeah, lots of different ways that we've inferred that there is more matter than what we've seen, and some of those things here, for example, like the CMB, tells us that also the matter that we're seeing is not very young. Okay, all of this is gravitational evidence for the existence of dark matter. But then the question is there non-gravitational interaction? And if so, what are the properties of dark matter? If it's a particle, I want to understand how it's, what's it out. Okay, and of course, this is a very, very wide topic. Lots of people have looked into this, and the mass range of the parameter space is huge. Ranges from very, very massive, 10 solar masses or more, or it can have stuff that's, micro EV or even much lighter. So yeah, lots of different things, and depending on where you're looking, there's a bunch of different models that would nicely explain it. So you have to limit yourself to the range if you're gonna make a specific study. And for me personally, I've mostly been focused on this range over here. And this is also the range I'm going to be focusing on in this talk. So think a few MeV to a few GeV mass. So yeah, this is kind of a bit of a landscape for what we're talking about. Okay, so if you want to look for non-gravitational interaction of dark matter, there's a few different ways you'll want to look for signatures, and depending on the type of interaction that you're talking about, the methodology will be different. So, for example, you're going from, you look at this diagram here, going from top to bottom, you have dark matter interacting with a standard model particle, and something happens in the middle, and then you get a dark matter particle, standard model particle. This could be an elastic or inelastic interaction. I have little labels here, which I heard some complaints about. But this is on Earth or in space. This is kind of, it's not always true. Sometimes direct interaction could happen in space. Indirect interaction could happen in Earth, but usually, just like as a rough guideline, this is kind of where you expect. And just a nice picture here from LuxLZ, where it describes an example of direct interaction. You have an incoming particle interacts with this scintillator material. You get some particle emitted, electron or photon, and then the dark matter particle just scatters off and exosphere detected. And this is direct because you're actually interacting with materially through temperature. Okay. You can also go on the center from right to left. So you would have dark matter annihilating, giving you two standard model particles, or it could be a dark matter particle decaying to two standard model particles. And yeah, this is usually you see it in space, not necessarily. But one example is the Fermilab telescope, for example, gamma ray survey, and then you look for kind of excess over what you would expect from the galaxy. Okay. Finally, I should say, yeah, if you have a indirect, if you're looking for indirect detection, the way you would characterize that is a little bit dependent on what you assume the output is going to be. So, if you have photons or electrons or hadrons or neutrinos, then, that kind of dictates what kind of, instrument you're using. Finally, the last direction is if you're going from left to right. So you have standard model particles interacting and then giving you maybe two dark matter particles, or it could be a dark matter particle and a standard model particle, or it could be even two standard model particles. but then the dark matter is living in the blob in the middle. So this is stuff that we usually look for in colliders. For example, Atlas or Bell, like talk about more, and of course a bunch of other colliders as well. Okay. So I want to shift gears now a little bit and just talk a little bit more about Bell, and specifically chiral Bell. So Bell 2 is a detector on the ring of superket B. Superket is it's an accelerator. They accelerate electrons, positrons, and then I think there's a circumference of like 3 kilometers or something. And they accelerate them, and then they collide in the where the Bell 2 detector is. And so this is kind of a nice schematic of what's going on here. It's an asymmetric detector. You have 7 GeV electrons from one side. You have 4 GeV positrons from the other side, and they're colliding at 10.58 GeV center of mass energy. And yeah, Bell has a very rich physics program. They're hoping to reach, the target is to reach 50 inverse attobarns of data. So this is a huge amount of data. It's very high luminosity. And one of the main physics goals for Bell is to study flavor physics, it's a B factory, so produce B bar. And yeah, they also want to do precision electroweak physics, dark sector physics. And okay, so given that it's a very high luminosity detector, there's a couple of nice things about it. First of all, being very high luminosity means that you can kind of lower your systematics. You just have a lot of data to work with. The other nice thing is that Bell is it's an lepton collider. They're colliding elementary particles. They're light, and so the signal is roughly, relatively compared to hadron colliders, for example, it's very clean. You don't have a lot of, you don't have messy jets going on. So it's somewhat easier to characterize what you're seeing, which is very nice if you're looking for dark sectors. Okay, so this is the Bell detector. Chiral Bell is a very nice proposal that a lot of people have done, have put forward. And the idea is that just take the electron beam and just polarize it. And the aim is to get to like around 70% polarization, which is like that's like the realistic goal. Obviously, the higher the better. And yeah, there's lots of arguments for why you would want to do that. You can do you can do a richer electroweak program if you have access to left-right asymmetry. You can look at things like the tau anomalous magnetic moment, G-2. And also you can have a more comprehensive dark sector search. So hopefully I'll convince you either. Okay. So I want to talk a little bit about the dark bosons that we're looking for here. But before I get to that, I just want you to put in context the signals that we're looking for. So the main signal that we're interested in looks like this. So if you're talking about Bell, you have electrons and positrons colliding them. And what we're looking for is a signal where you see the detector just one photon. That's the diagram on the left. And the boson here, this is a dark boson, which could be the dark matter, and then miss it. Or it could also be a mediator. So, this could indicate the stuff. But then, the idea is that it could just indicate some invisible stuff. So this could be a mediator coupling to dark matter, and it's dark matter stuff. There's a secondary signal that one can think about, is that if it's also mediating a diagram like this, where you have electron positron, you have the boson, and then you get some fermion pair. And okay, how do you distinguish this from other standard model particles, because this can of interactions, and this can happen in the standard model. And I'll get to that later. Okay, so this is these are the processes I want you to keep in mind. So now, okay, what is what are the bosons that we're looking at? So here I'm specifying more to a vector boson, so spin one. So if it is spin one, then you can write a generic coupling. So here, this is Lagrangian coupling it to electrons. You have some vector coupling, you have some axial coupling. And the vector here itself, I want it to be massive. So I'm just giving it a mass, but I'm not really caring too much about how it's getting that mass. It could be from a Higgs mechanism or a Stickleberg mechanism. But the important thing is, I want it to be light. So it's a lot lighter than the Z boson. And that's because I also, I want it to be, if it is the particle that I'm producing, I want it to be able to produce it at Bell, which has access to only 10.58 GeV. So, for now, assuming that it's, only scanning for masses much lighter than the Z mass. Okay, so this is somewhat generic, but you can then specify some kind of benchmark model for how you're looking at this. So you can look at just kinetic mixing. So if you have a dark photon, you would have, if you have some field, tensor for the dark photon, it's coupling to the hypercharged field, then that you just have kinetic mixing with the regular photon. And if you're in this light mass range here, it turns out that what you get is mostly vectorial coupling. So you have this here, and the axial coupling is suppressed by an order of 10 to the negative 3. But it's still there, but it's pretty small. You can also look at, so this is kinetic mixing. You can also look at a model where you have mass mixing. So if you can imagine something like the regular Z boson, but this is just it's very similar to it. It's just a dark Z boson, and it's just mixing with have mass mixing with the regular Z. And okay, this works out to have mostly axial coupling. This coupling, these expressions here are actually very similar to what you would get from the standard model boson. The only difference is that you have this extra on Z. And this, okay, if you specify the UV theory a little bit more, then you can get a little bit more mileage from this. You can kind of characterize this as a ratio of the masses of the Z and the dark Z times some parameter. Okay, another model is if you can also imagine some boson that only couples to right-handed fermions. This is somewhat motivated by there are certain anomalies that one can explain if you have vectors like this. The issue with a model like this is that I believe you would need to have extra fermions. And so it's like, okay, somewhat modeled depending exactly how it would look like. But one thing to note is that atomic parity violation limits give you a nice constraint on the sum of PA and UV. And finally, just for completeness, you can also think of some more generic model where you have some mixture of kinetic and mass mixing. So this is something that you can have. But I'm not going to focus on this, so I'll only focus on the top. Okay. So now kind of specializing a little bit more to dark vectors, how can you actually see them with parallel belt? So going back to the main signal, so single photon, and now you have a vector on the other side. And here are your beams. You have 7 GeV electrons, 4 GeV positrons. This is unpolarized. The positrons are unpolarized, and the electrons 70% polarized. And okay, you have 10.58 GeV, center of mass energy. And you go ahead and calculate the cross sections. So let's now assume, just for simplicity, assume the electron beam is fully polarized. And go ahead and calculate the cross sections. What you will find is you have some expression here that is dependent on the energy, the mass, and also depends on the angle. So you can think of this as like a d sigma d cos theta. It does depend on the angle. But you also have this, but there's no dependence here in this term on polarization. So this does not depend on polarization. So what this tells us is that the polarization dependence is all contained in here, whether you have the plus or the minus. And this also tells us that depending on what polarization you have, you're only going to change the amplitude of your signal. Or if you're looking at a detector, at a detector level, you're saying, I'm going to change the number of events that I'm seeing if I have mostly right or mostly left. But the important thing is that angular distribution is not changing. Okay, a more realistic case is, so Bell is aiming for mostly like 70% polarization, which the way that's defined, you can think of that as maybe 85%. The beam is 85% right-handed electrons, 15% left-handed electrons, and then the positron beam is unpolarized. And then you can go ahead and calculate the cross section. Okay, and then you get some expression here. And then the way it's going to work is that half the time they'll run it at this polarization configuration, and then the other half of the time it'll flip. So it'll be 15% right-handed, 85% left-handed, and then this is what I'm going to call the left-handed cross section, but really mostly left-handed. And then okay, you get less. So what we would expect is that my signal, so to speak, is that I would see more right-handed events than left-handed events. Okay, so all of that was for a boson that is a vector. But what if the boson is a scalar? What if it has spin 0? So if it's spin 0, okay, so it could be scalar or even pseudoscalar. So generically coupling it to electrons, you can have a generic structure like this, GS and GP. And you can also couple it to photons with kinetic mixing. And it turns out that you have something like this to calculate the cross sections. What you get is that they're the same, whether it's right-handed or left-handed. And okay, this may be for sight tells us that you can't really learn a lot from, if it was a scalar, you can't really do much if you have a polarized beam. But of course, having, if you do actually run the experiment and see the same number of events, then maybe that is that what you have, if it does exist, that it's a scalar and not a vector. But also within those segments here, there's an angular distribution that is different from backgrounds. So okay, just Bell itself can also be a different for things like this, just not necessarily parallel, but Bell is still a big group because this angular distribution is kind of different from backgrounds. Okay, and I did mention that there's another signal, possible signal. So if your vector, so, it's just sitting in the middle here as a mediator, what you would the thing that the quantity that you look for is this left-right asymmetry, which I've put down the definition here. It's just, you can think of it as the difference between left-handed minus right-handed events, and just normalize it to the total number of events. And if you can imagine a process like this, and then what you have in the final state are could be any fermion, just not the electron. Then this is the only, at tree level, this is the only process that you can have. And then, okay, you could have a pretty simple expression. And some people have looked at things like this, where some people at Bell looked at processes like this. And the idea is that in the standard model, so forget about any dark vectors, just standard model processes, you still will get a left-right asymmetry. if this is mediated by the Z. And I think this is not actual measurements, it is still simulations, but what they did is that they quantified, they can run some measurements on how much left-right asymmetry you would expect just from the standard model process, and then you can also get some kind of sensitivity. And so if you know the sensitivity to the standard model process, then this can also give you some kind of bound, upper bound on this combination of GA and GD, if you do assume that there is a dark boson mediating this effect. You can do also something similar if you have, if the final state is an electron, it's just that you would have an extra diagram, you have a T channel, and the expression for left-right asymmetry is just a little bit longer, but it's not complicated. And the people at Bell have also looked at Bell's sensitivity to left-right asymmetry like this, but only in, if you have a standard model process. But then same idea, you can take that and then use it to also get a bound on your GA-GD combination. And roughly what you would get is something that kind of looks like this, where you're not allowed to go anywhere here. That would give you too much asymmetry that they would have seen at Bell if that was the case. So you have to be somewhere inside those non-shaded regions. Okay. The thing about those signals, though, is that the sensitivity that you get from those is actually not subreading compared to the main channel that we're interested in, which is the monophoton channel, in the mass range that we're looking at here, which is less than 10.5 dB. But this channel is interesting, or at least we think it is interesting, if you are looking at higher range masses, and you can, for example, if you think that you can produce the boson off shell, and then maybe because of the neutrinos or something, then it's probably important to look at processing for this. So just to focus more now on the main channel, and I want to talk a little bit now about the backgrounds. So I'm just listing here a bunch of the important backgrounds that we're considering. So the dominant background is electromagnetic. So you can imagine electron, positron, you're scattering, and then you emit, you can emit maybe initial state or final state photon, and then you would see that, but you miss the electrons in the detector. Maybe they have too little transverse momentum or something like that. You would miss them, or if they're collinear. And so what you would see in the detector is just one photon, and that's kind of like the signal that I'm looking for. Or you could also have emitted two photons, but also have missed one of the photons. So that's also looks like the signal. You could also have electron positron annihilating, giving you three photons, miss one of the photons, see only one, or maybe you could have three photons. And that's kind of the idea with all the backgrounds, is that, okay, you miss everything, but you only see one of the photons. And okay, the electromagnetic background is most dominant. You can have, there's also an electroweak background. This is subleading, but it could become important if you have very high luminosities. So this is also important to look into. And it's particularly interesting to us because this background, given that it's electroweak, this process is spiral, so it is polarization dependent. However, it is an irreducible background for us because it has the same structure as the signal that we're looking for. And there's other backgrounds for like you can produce hadrons and a photon, or you can produce taus. But those things, given that the taus are heavy and the hadrons, you just get a lot of tracks from those things, and you can veto those tracks and it'll be okay. Unless the energy is too low, then it becomes a irreducible background. Okay, so if you take a look at all those backgrounds, and And basically, okay, look, simulate how many events you're gonna get just from the background, and you get some thought. But before I show that, just show me here a little schematic here of the detector, just to keep this in mind. So this is, if you think about it like a side view where you have one beam from here, one beam from here. And for the, the lab angle here, this is the scattering angle of the photon. And based on what photon eventually we're seeing, this is the expected number of events. And the structure that you see here, this structure that you see here with the arches, this is just from geometry of the detector. It's just a weird interplay between the geometry of the detector and free body final states. But essentially, this is stuff that gets missed somewhere in the end pass here. You also have this like line at the top here, and that's mostly due to just an inefficiency. So one of the processes was that you have E plus E minus, and then you get two photons. And that process, the photons will have to carry the total energy, right? Because they're massless. So they're kind of concentrated here up on the top. And it just so happens that the detector cells at Bell, even though both photons would have hit the detector fine, there's still like a 10 to the negative 6 probability that you would miss one of the photons. It's very low. However, we're talking about this is at 20 femtobarn, so this is very high luminosity. So it's still important. Okay. Also, to make this more realistic, you want to simulate also the resolution of each detector cell. So basically, this is mostly done actually by Carlos and Douglas. What they've done is they just applied a Gaussian smearing here and just to kind of simulate this resolution here of each cell. And now, okay, when you have something like this, what the analysis that you can do, at least first order, is just make a hypothesis for what the mass of your boson is going to be, and then based on that, you would know which horizontal strip the photon would be living at. And for each section of those things, then what you want to do is make a cut in your angle where you're gonna, this is the region that you're going to accept, and that cut needs to maximize signal to background. More accurately, it needs to maximize this statistic here, Z, and so for each mass hypothesis, you're gonna, this Z will maximize it. You're gonna need to take different cuts. So here's an example here where roughly you would want to take this cut here, where you see the region between the orange and the red lines it kind of doesn't have a lot of backgrounds. So I should say here that this picture of all the backgrounds, this is, I didn't say anything about polarization. This wouldn't look very different if I did include polarization effects, and that's because most of these backgrounds, most of these events are actually coming from the dominant electromagnetic background. And however, there is some polarization effect here from the signal itself, because the signal, although the signal is not really dependent on its polarization doesn't really change its angular distribution, it does change the magnitude, and that does still, when you actually do the analysis of making, choosing what your cuts are in the scattering angle, that does change it, because there'll be different cuts that would maximize the Z. Okay, so a nice way you can translate all of these is that, okay, once you maximize the Z for each of those, and you want to, you demand that it's, I don't know, 2 sigma or 5 sigma or whatever, and then you can translate those things here onto a, mixing versus mass plot. So this is kind of what you would get. Here on the vertical axis, this is just an effective mixing, which is defined like that on the left, just to take into account polarization, but also remain model independent. So, we don't have to talk about what, if it's a dark photon or could be dark Z or whatever. And if you're at 20 inverse femtobarns, then you're this black line here. There's no difference really between polarized and unpolarized analysis. They look the same, and that's because at that luminosity, the electrolytic process isn't really important enough to make any changes. But if you run Bell at say 40 inverse nanobarns, a little bit closer to their target, then the limit goes all the way down here. And then at that very high luminosity, then or integrated luminosity, then the electrolytic process does become important. And then you see that there's a little bit of a difference if the beam is mostly left-handed or okay. But either way, whether it's polarized or unpolarized, both of these bounds here show that Bell actually does promise a very good sensitivity to dark photons or chosen. Okay, but still here, the difference isn't huge. So, okay, why polarize the beam? Has to be more interesting than that. And you can look at the plane here at GB versus GA. And if you take a slice in that previous plot at say 100 MeV, and then look at a plot like this, and then, okay, based on how you can kind of think of this like a comparison where you could, in one scenario, you're running Bell at only 40 inverse unpolarized, and you take 40 inverse out of one theta, then you have this circle here and everything outside it is excluded. And you can take the other scenario where instead of taking 40 inverse out of barns of unpolarized data, I'm going to take 20 inverse out of barns right-handed, 20 inverse out of barns left-handed. And what you'll get from each are those ellipses here. And if you don't see a signal after you run that much, then you exclude the stuff outside. The plots in the green dashed lines, this is where you would expect to live if actually there was a dark boson, a dark vector that was, for example, here, that if it was a dark photon, that fixes the relationship between GA and GB, and would have to live somewhere here. And this is hidden, but this is the right-handed vector, and this is the dark Z photon. And now it kind of gets interesting if you ask the question, okay, so what would we see if we run Bell, take this much data, and then we see enough signal events that we can declare a 5 sigma discovery. Then on that same plot, so this is now assuming a 5 sigma discovery. This is a slightly different mass hypothesis. Then you can still think about this as a comparison of unpolarized versus polarized, where if you ran it for 40 inverse autobarns and it was unpolarized, let's just look at the dark photon case here. You would expect, okay, that tells you that your signal is somewhere in the black-gray circle group. The shaded region is just plus minus 1 sigma. So the preferred region is this circle here, but it doesn't really tell you anything about, there's a degeneracy here, right? It can be anywhere on that circle, and that will be consistent. So it doesn't really tell you anything about whether the boson is a dark photon, dark Z, or something else. So it hasn't really told you much about its Lorentz structure. However, if you take if you do the same amount of data, just split it between right-handed and left-handed, and now remember, this is assuming that you do see a signal, you're seeing it in both. What you would get is preferred regions in those ellipses here. And given that you're seeing a signal, and if you're seeing it in both, then what that tells you, you get a partial breaking of the degeneracy here, where instead of living on the whole curve, now you have to live on the intersection. And so that kind of limits you to like those regions here. You still have a little bit of degeneracy, but much less. And it's somewhat nice because yeah, so this is somewhat, yeah, it limits you to those, intersection regions. And then for, okay, each model, those intersections will also lie, on that green line. Finally, there's this, the red shaded region. This is, you can also do a left-right asymmetry. You can calculate that quantity, which doesn't fix the GA and GV themselves, but fixes their ratio. So you get those, just like essentially you get lines. This, yeah, so you can also calculate the left-right asymmetry in this case. Okay, and then you get those red regions. Okay, I think that brings me to the end. And just to summarize, so we're mostly interested in those monophoton processes. You have P plus and minus, giving you a photon and a boson. Such processes, Bell itself is already very, very good at looking at things like this, as you saw, even if it was unpolarized sensitivity. But if you do polarize the beams, then you get access to two new things. One is some distinguishing between, some distinguishing for the spin of your dark boson. It could be either a vector or a scalar. And the other thing is also a little bit of, you kind of break this degeneracy and a little bit more information about the Lorentz structure of what you have. If it's is it mostly kinetic mixing or mass mixing and so on. The backgrounds that we considered here, like I said, there's a lot of them are dominated by electromagnetic processes. And the backgrounds from geometry, you can't really do much about that because that's just how the detector looks like. But some things like backgrounds from inefficiency, you can kind of lower that. Especially that strip at the top, you can lower that background. And yeah, the last thing I want to say is the electroweak background. That in itself is actually an interesting target. Well, we call it a background here, but it's the process that you're looking at. This is also an interesting target for chiral Bell because you can apply essentially very similar machinery to look into the Z coupling to neutrinos and kind of get a precision measurement on the theta W for in the neutrino sector. Or you could also consider producing a heavy dark boson off shell in a process like this. And also kind of think about how you can constrain something like that using parallel. And that is all. Thank you.
Questions?
Going back to the exclusion plot you have, for a lot of the masses, it seems like it's relatively flat with a small dip. Could you maybe talk about, like, I've never seen an exclusion plot like that's just flat like this. Why would that be for such a wide range of masses?
Yeah, so this is actually kind of similar to Ballard's exclusion plot as well. And the reason is if you look maybe here, this would make somewhat more sense. So most of the region where it was flat, that was region that was largely dominated. So if that mass range was largely dominated. So you had lots of backgrounds in there, and it doesn't really make a big difference. The mass that you're taking. If you change the mass, the background is still going to be very, very big. And of course, remember that this is a log scale. So this is all of that is the same as here. But yeah, essentially the answer there is that the regions on the left are, they're weaker, the limit here is weaker than here, because we have just the backgrounds are bigger. And then you get to this dip here, this is essentially this region here. So this is where you have almost no backgrounds, so you get much better sensitivity. And then towards the end, then you're kind of going towards the top here where you do get backgrounds again. And yeah, but if you're all the way here, then you kind of, there's actually lots of backgrounds, so we kind of cut it off actually before that, because then, yeah, you come on residence and start producing these.
Additional questions?
You said, you mentioned scalar dark matter and how, that would be consistent if you saw the same, rates for left-handed and right-handed polarized beams. And then you briefly mentioned something about, relating that to, like, if you did see that, you could say something about vector dark matter. Would you be able to say something about vector dark matter globally, or just models that couple to the electron in the way that you showed?
Yeah, I think it's pretty generic, because at that level, you're not really, we haven't specified anymore. All I said there is just, I'm deciding what spin it has. So as long as it's a vector versus scalar, doesn't matter what the model is, it's still going to, this statement will still be true.
Okay.
So if you do see the, yeah, if it is exactly, exactly left versus right. Yeah, the statements that you would make are either it's a scalar or it's not coupling in a chiral way to your stuff. So it's still, yeah, like that doesn't necessarily mean that, oh, I know for 100% that what I have is a scalar, I mean, it could also just not exist. But yeah, I don't think it's modeled within that level. Okay.
Just curious, what is A of E in this plot? In the line A, E.
Sorry, can you say that again?
There is a minus 64 and then the A suffix E. Yeah,
that is,
I'm just curious, what is that?
I don't really remember what measurement this is. It says some other measurement. I can't really
Okay.
remember which one this is.
It's fine.
I don't really know. Yeah. Yeah, I can just look at the paper and see what it is.
Any other questions? Okay, let's thank, yeah.